Alright everybody, what's up? This video we are going to look at improper integrals. So let's go ahead and get started. So if we have the integral f of x dx from a to t, if that exists for every number t greater than or equal to a, then we have the integral a to infinity f of x dx is equal to the limit as t goes to infinity of the integral a to t of f of x dx. So what we're doing is, see, the integral here is going from a to infinity. And you can't evaluate a function at infinity. So what we're doing is we're taking this infinity right here and we're replacing it with t, and we're taking the limit as t goes to infinity. All right, and then the same thing down here. If the integral t to b of f of x dx exists for every number t less than or equal to b, then the integral negative infinity to b of f of x dx is equal to the limit as t goes to negative infinity of the integral t to b f of x dx. So what we're doing here is we're taking the negative infinity, we're replacing it with t, and then we're taking the limit as t goes to negative infinity. All right. Now, if we have the integral a to infinity f of x dx and negative infinity to b f of x dx are called convergent if the corresponding limit exists, and divergent if the limit does not exist. So if the limit exists, it's convergent. If it does not exist, it's divergent. And if both of these integrals here of f of x dx from a to infinity and negative infinity to a are convergent, then we define. So what happened here is we have the integral from negative infinity to infinity. So what we have to do is split that up. We're going to go from negative infinity to a f of x dx plus the integral a to infinity f of x dx. And we'll talk about this more, splitting it up, when we get to the example. So let's go ahead and look at an example. So we want to determine if this integral here is convergent or divergent. So let's go ahead and work it. So we've got the integral 1 to infinity of 1 over x dx. Well, what do we have here? Well, see, we're going from 1 to infinity. So this is going to be the limit as t goes to infinity of the integral 1. Now, you see the infinity here? We're replacing that with t because we're going to have t goes to infinity. So that's t of 1 over x dx, which is equal to the limit as t goes to infinity of natural log absolute value of x from 1 to t. And now we just evaluate this thing. So this is equal to the limit as t goes to infinity of what? Well, look, it's the limit of this thing right here. So we know how to evaluate this. This is going to be the natural log of t minus the natural log of 1. All right, so let's take the limit as t goes to infinity. Well, to make it a little easier, we know this is equal to the limit as t goes to infinity of just natural log t, because this term here, this natural log of 1, that goes to 0. Remember, natural log of 1 is just 0. So what does this equal? Okay, the limit of natural log t as t goes to infinity. Well, think about what the graph of a logarithmic function looks like. It looks like this, doesn't it? All right, this is something that we should know already. So look what happens. This is your t-axis. As t goes to infinity, as the t values get larger and larger, you can see the graph goes this way. And what's happening to the y values? Well, they're increasing, right? They're going to infinity also. So this is equal to infinity. So we would say this is divergent. All right. All right, so let's look at the next example. All right, so how about this one? Evaluate negative infinity to 0 of x ex dx. All right, so we have what? We have the integral from negative infinity to 0 of x e to the x dx. I just copied the problem down again. And so this is going to be what? The limit as t goes to what? Well, t has to go to negative infinity. See that? T has to go to negative infinity. So t goes to negative infinity, the integral 0, and the negative infinity here gets replaced with t. And that's going to be x e to the x dx. All right. Now, what do we have to do now? We've got to integrate this thing. So how do we integrate it? Well, this we need to use parts. So we're going to let u equal x, dv equals e to the x dx. And so du is equal to dx and v is equal to e to the x. And so this is going to be the limit as t goes to negative infinity of all of this. All right, so what is this? See, we're just working with this part right here. We're integrating it. And so that's u times v, so x times e to the x, and that's going to go from t to 0 minus the integral, and that's going to be what? T to 0 of e to the x dx. And so now we're going to get the limit as t goes to negative infinity, and all I'm going to do right now is just integrate this thing. So that's going to be x e to the x from t to 0 minus e to the x from t to 0. All right. All right, so let's see what we get now. So this is going to be the limit as t goes to negative infinity. All right, so let's do this. Let's plug the 0 in for x. So that's going to be 0 times e to the 0 minus t times e to the t minus, and let's put this in parentheses because it's going to be minus this whole thing. That's going to be e to the 0 minus e to the t. All right. So yes, this thing can get kind of messy if you let it. All right. So this term here goes to 0. And so that's going to leave us with the limit as t goes to negative infinity of negative t e to the t minus 1. See, minus e to the 0. E to the 0 is 1. And then plus e to the t. All right, so now what we have to do is we have to take the limit of this thing. All right, we've got to take the limit of this thing. All right, so how in the world do we do that? All right, so first off, this, we know see, we're going to take the limit of each term. We're going to do the limit of this, this, and this. Well, we can see this one, that's just -1. That's going to just give us -1. And this one right here, what is that going to give us? All right, so let's think about that. Let's just come down here. Let's come down here and work that. So if we do the limit as t goes to -infinity of just e to the t, I'm just looking at this term, and then we'll do this term next. All right, so t is going to -infinity. So look, let's just kind of look at it this way. You see that? If that's -infinity, that means that's a big number with a negative sign in front of it. So that would be like doing 1 over e to the positive infinity. It would be a big number, okay? And I know you cannot plug the negative infinity in, okay? Just pretend like this is like -1 million, -1 billion, -1 trillion, and so on. All right, so you see how the denominator here is getting bigger and bigger and bigger, but the numerator is 1. So we can see that this goes to 0, that this entire fraction here is going to 0. All right, now let's look at this part. The limit as t goes to -infinity of -t e to the t. All right. So what is this one going to look like? Well, if you think about when you learned how to do L'Hopital's rule, what we'll do here is we will rewrite this thing as -t over e to the -t. I'm just bringing this e to the t down below, because I mean, look what happens if we take the limit as t goes to -infinity. This term right here, that's going to infinity. That's just getting larger and larger. And then we showed over here on this one how this one's going to 0. Well, we can't do infinity times 0, so we're rewriting it like this. All right, so now look at this. We can take this negative and put it up here. So if t is going to -infinity, the numerator's going to infinity. And look, the negative and negative, that's going to be a positive. So the denominator's going to infinity. So we have infinity over infinity. So that allows us to use L'Hopital's rule. So that's going to be the limit as t goes to -infinity of -1 over -e to the -t. And the negative over negative makes a positive. And what happens? Well, the denominator's getting larger and larger. That's a negative in front of the t. T's going to -infinity, the negative and negative. That's a big number, positive. So this whole fraction is going to 0. So we can see that this term is going to 0 also. And so what does that limit equal? Well, that's 0 minus 1 plus 0 equals -1. And so there's your answer. So, the limits, some of these limits, they might be some of the more difficult limits that you have to evaluate. But, that's just what it is. You got to think of all the rules you've learned with limits and going to L'Hopital and even doing L'Hopital's rule. All right, so how about this one? We want to evaluate. So this is the one where we have -infinity to +infinity. So we have -infinity to +infinity of 1 over 1 plus x squared dx. So this is the one that it was talking about, where this one, okay, where you have to split it up at some number a. All right. Well, we know this function's continuous everywhere. Okay. So if we look at this, let's split it up. Let's split this thing up, negative infinity to 0. So I'm going to split it up at 0. Yeah, you know, if you wanted to, you could split it up at 1. But why? Usually 0 is the easiest. Okay? So that's 1 over 1 plus x squared dx plus the integral 0 to infinity of 1 over 1 plus x squared dx. All right, so we need to evaluate these two. So for something like this, instead of working all this out together, what I like to do is I like to take this part, solve it, this part, solve it, and then add the results together. Okay, just take it one step at a time. So first, let's do 0 to infinity of 1 over 1 plus x squared dx. All right, so what does this equal? Well, this is equal to the limit as t goes to infinity, see the infinity, the integral 0 to t, 1 over 1 plus x squared dx. And that is equal to the limit as t goes to infinity of inverse tangent x from 0 to t. All right, remember the antiderivative of this is inverse tangent. So we are going to get the limit as t goes to infinity of, okay, we're taking the limit of this, so we've got to work this out. So that's going to be inverse tan of t minus the inverse tan of 0. All right, so what does this equal? Well, what's the inverse tan of t as t goes to infinity? All right, so do you remember how to do that? Inverse tan, t is going to infinity. Well, do you remember? Let's come down here. You remember what the graph looks like? Whoop. And this is pi over 2. This is negative pi over 2. And the graph of inverse tangent looks like this. So we can see as t goes to infinity, inverse tangent is approaching pi over 2. So that's pi over 2 minus, and then the inverse tangent of 0 is 0. And so that's pi over 2. All right. So now let's look at the other one. We've got negative infinity to 0 of 1 over 1 plus x squared dx, which is the limit as t goes to negative infinity this time of t to 0 of 1 over 1 plus x squared dx. And so that's going to be the limit as t goes to negative infinity of what? Inverse tangent x from t to 0. And I'm going to need to erase this. All right, so this is going to be the limit as t goes to negative infinity. All right, and that's going to be the inverse tangent of 0 minus the inverse tangent of t. All right, so this is 0 minus, and then I don't know if you remember, let's just go ahead real quick. That's pi over 2, negative pi over 2, and the graph looks something like that. So as t goes to negative infinity, you can see that inverse tangent is approaching negative pi over 2. So that's negative pi over 2, which is just pi over 2. All right. So that's going to give us negative infinity to infinity of 1 over 1 plus x squared dx is equal to, well, remember, it equals this. So what did this equal? That equaled pi over 2, and this was equal to pi over 2. And so that's pi over 2 plus pi over 2, which equals pi. And there's your answer. All right, so there was an example of each one where we're going from a to infinity, negative infinity to some number b or a or whatever it is, and then an integral from negative infinity to positive infinity. Okay, that was an example of each. Just remember, if it's going from negative infinity to positive infinity, you're going to have to split it up. All right? All right, so let's take a look at this. So if f is continuous on AB, notice the a is included, the b is not, and is discontinuous at b, then the integral a to b f of x dx is the limit as t goes to b from the left. Okay, so t is approaching b from the left, the integral a to t f of x dx. And if f is continuous on a to b, notice the a is not included but the b is, and is discontinuous at a, then the integral a to b f of x dx is the limit as t approaches a from the right of the integral t to b f of x dx. Now, where some students may get this confused is, well, how do I know coming in from the left or from the right? How do I know to take the limit from the left or the limit from the right? Well, I mean, it's pretty easy, I think. So, if you just draw it out like this, okay, you're in this interval here. The a is included, the b is not included, okay? So we're staying in this interval here, okay? We're from a to b. We're not going to come outside here. We're between a and b. So if you just draw it out like this, the b, it's discontinuous at b. So we've got to approach b from what? From the left-hand side. So we've got to be inside the integral. So that tells you the left-hand side. And then the same thing here. There's a, there's b. The a is not included, but the b is. So how do we approach a? Well, we got to come from inside the integral. So we've got to approach from the right-hand side. And that's an easy way to know the left and right. All right, and then if we have the integral a to b f of x dx is convergent, okay, so this integral is convergent if the corresponding limit exists and divergent if the limit does not exist. And if f has a discontinuity at c, where c is between a and b, and both of these integrals, f of x dx, from a to c and c to b are convergent, then we define the integral f of x dx from a to b is equal to this. All right, so what this is saying is that we're integrating from a to b, but there's some number c between a and b where the function is discontinuous. All right, so let's take a look at some of these examples. All right, so here we go. So we're going to do an example of each one, okay, of each one of the problems. So you can see that this function here is discontinuous You see that? It's discontinuous at 2. F of x is. So, we have 2 to 5 of 1 over the square root of x minus 2 dx is equal to the limit as t approaches 2. Now from what side? The right or the left? Well, remember what I showed you. 2, 5. It's discontinuous at 2 because that would give us 0 in the denominator. And you can see we got to come in from the right. And that's of the integral, and that's going to be t to 5 of 1 over square root of x minus 2 dx. And so now we have to integrate this thing. You're going to have to use u substitution. Okay? So you're going to have to let u equal x minus 2, du is dx. And so this is going to be the limit as t goes to 2 from the right of the integral. Now, let's do this. Okay? I think it's easier just to come up here and do this substitution just off to the side. So this is going to be u to the negative 1/2 du. See that? So I replace this with u, and that's u to the 1/2. Move it up, that's u to the negative 1/2. And then dx is du. And so this is u to the 1/2 times the reciprocal of your exponent, 2. And so this is going to give us what? 2 times the square root of x minus 2 from t to 5. All right. So I hope that made sense. I kind of skipped a lot, but this, you should know how to do this at this point in calculus. Okay, you've done this before. All right, so this is the limit as t goes to 2 from the right. All right, so that's going to be 2 times the square root of 5 minus 2 minus 2 times the square root of t minus 2. Right? See, we're just evaluating this integral right now. That's what I get here. Plug the 5 in, minus, and then plug the t in. Now let's take the limit of this thing. So, well, this is what? This is 2 square root of 3 minus 2 times the square root. Now to take the limit of this thing, I can just plug the 2 in. 2 minus 2. Now this is 0 right here, so we just get 2 square roots of 3. And there's your answer. All right, so let's look at another one. I hope I didn't confuse you much on the integral stuff. Okay, I just kind of went off to the side and jotted that down. All right, so let's look at this one. All right, so determine if the integral 0 to pi over 2 of secant x dx converges or diverges. All right, so let's see, we've got 0 to pi over 2 of secant x dx. All right, so this is going to be the integral 0 to t. So let's think about this. Remember, secant x is equal to 1 over cosine x. All right. Now, the cosine, so we got 1 over cosine 0. That's 1 over 1. We're good there. Secant, so secant is not undefined at 0. But if we do 1 over cosine of pi over 2. Remember, pi over 2, that's 90 degrees. Cosine of pi over 2 is 0. So that gives us 1 over 0. So it's undefined at pi over 2. Okay? And I forgot to write the limit. That's the limit as t goes to pi over 2 from what side? Well, let's see. We are 0 to pi over 2. It's discontinuous there. It's continuous. So we're coming in from the left-hand side. All right. So, you may have to do some of this. Just kind of go off to the side and jot this down. And so that's going to be the integral 0 to t of secant x dx. All right. All right, so what do we get? Well, we get the limit as t goes to pi over 2 from the left. Now let's integrate this thing. So what do we get when we integrate it? Well, that's going to be what? The natural log of secant x plus tangent x, right? And that's from 0 to t. All right, so that's one of the integrals you need to remember. The antiderivative of secant x is natural log secant x plus tangent x. That's part of your the integral tables. Your table of integrals that you're supposed to know. All right. So now we get what? We get the limit as t goes to pi over 2 from the left, and that is going to be the natural log of secant t plus tangent t minus, make sure I'm putting all this right, minus the natural log of secant 0 plus tangent 0. All right, so let's look at this. So let's look at secant t and let's look at tangent t as t goes to pi over 2 from the left. So one thing that we can do real quick, and this right here shouldn't take you long to do. All right, so we know that this is the graph of cosine. And so remember here, this would be the graph of secant. Okay, just sketching it in real quick. And then remember real quick, there's negative pi over 2, there's pi over 2. And this is the graph of tangent. There's your graph of tangent. So you can see that as we come into pi over 2 from the left, what is secant doing? It's going to infinity. And tangent is also going to infinity. This all in here, we got a big number plus another big number. That's the natural log going to infinity. This whole thing here goes to infinity. So really it doesn't matter what we have here. This is going to infinity. This is divergent. Okay, but let's go ahead and do this. What's the secant of 0? Well, that's 1. This is 0. And the natural log of 1 plus 0, or the natural log of 1, this whole term here goes to 0. Okay, just to show you that. All right, but yeah, this one here diverges. Let's write diverges. right, so let's take a look at another one. All right, so this one's a little bit different than the one we just worked. So we've got 0 to 3 dx over x minus 1. Okay, so this one is going to do what? This one's like right here. See that? From, what was it, from 0 to 3? Well, the function is discontinuous at a number between the 0 and 3. You see that? We're going to have to split it up. So if you look at this, you can see this thing here is discontinuous at x equal 1. You see that? So we're going to have to split this up. 0 to 1 dx over x minus 1 plus what? 1 to 3 of what? Dx over x minus 1. All right. All right, so how do we go about solving this thing? Well, let's do each one of them individually. Okay, so let's start out with this one. So we've got 0 to 1 dx over x minus 1 is equal to the limit. Okay, so the limit as t goes to 1 from which side? Okay, remember how I showed you 0 to 1, it's discontinuous there. So we've got to come in from the, let's see. All right, so yeah, we're coming in from the left. All right, of the integral. Let's see what we got. 0 to t dx over x minus 1. All right, so this is the limit as t goes to 1 from the left. And what's the antiderivative of this? Well, that's going to be what? Natural log, right? Natural log, absolute value, x minus 1, and from 0 to t. All right, so this is going to give us the limit as t goes to 1 from the left of, that's going to be the natural log, t minus 1 minus the natural log, absolute value, 0 minus 1. All right, so let's think about this. All right, so we know here that's 0. That's just the natural log of 1. 0 minus 1, that's negative 1. We're doing absolute value, that's 0. So let's look at this part. What's happening here? We're approaching 1 from the left-hand side. Okay, approaching 1 from the left-hand side. So what does the graph of this look like? We can look at the graph, or we can look at, we're plugging numbers in, like I don't know, say 0.9, right? Because we're coming into 1 from the left-hand side, so that would be numbers like 0.9, 0.99, 0.999, and so on. So what's happening to this? This number in here is, if we plug the 0.9 in, that's going to be negative 0.1, but then we take the absolute value, that would be 0.1. Plug in 0.99, that would be 0.01, natural log of 0.01, and then natural log of 0.001, natural log of 0.0001. So what's happening here? Well, here's 1 right here. So the graph of this would actually look something like this, okay, with the vertical asymptote here. Because remember, you can't take the natural log of 0. It's just shifting. See, here's the normal graph of a natural log function. So that minus 1 is just shifting this over 1 unit, okay? So, this would be 2, and over here it's 1. We're just shifting this over 1 unit. So you can see as we're getting closer and closer to 1, to this right here, what's happening? Well, this is going to negative infinity. So this is going to negative infinity. All right. So we can just say this diverges. And you might be thinking, yeah, but you didn't do this one. We don't have to. If this one diverges, we can stop. We don't need to evaluate this one. Okay? All right, so, so that's what it is. The closer we get to 1 from the left-hand side, remember, we're not taking the natural log of a negative number. That's why we have these absolute values. We're taking the natural log of a positive number. So as, we're taking the natural log of like 0.1, 0.01, 0.00001. So what happens when we're taking the log of numbers that are getting closer and closer to 0? Well, the logarithm is going to negative infinity. All right. All right, so this is the last example. We want to evaluate 0 to 1 natural log x dx. All right. So if I have 0 to 1 natural log x dx, well, it's not continuous at 0, is it? We can't take the log of 0. So this is going to be equal to the limit as t goes to 0, and that's going to be t to 1 natural log x dx. Now, we're approaching 0 from which side? Well, like I said, just come up here and draw it if you need to. See that? So we're coming in from the right-hand side. All right. Now, we need to integrate this thing. So, look, what I like to do here, I like to just, well, I mean, it's not so bad with parts, but let's just do parts. We're going to let u equal natural log x. V is equal to, dv is equal to dx. So du is 1 over x dx, and v is equal to x. All right, so this is going to be the limit as t goes to 0 from the right, and that's going to be what? Let's see, that's going to be u times v, so x times natural log x minus the integral, and that's going to be 1 over x times x dx. Whoop, and I forgot to put t to 1 and t to 1. And so this is going to be the limit as t goes to 0 from the right of x times natural log x from t to 1 minus the integral t to 1 dx. And so let's integrate this thing right here. So that's the limit as t goes to 0 from the right of x natural log x from t to 1 minus x from t to 1. All right, so what's going to happen here? Well, let's plug the limits in. So that's going to be the limits. T goes to 0 from the right. All right, so that's going to be 1 natural log 1 minus t natural log t, okay, minus, and that needs to be in parentheses, 1 minus t. All right. So let's let's see what happens here. All right, so we can eliminate some of these things pretty quick. So we know that's 0. And we know, so when we take the limit here, that's going to be 1 minus 0. So we can just take the 0 and plug it in for t here. This is the one, this one right here is the one we need to look at a little closer. So we're going to need to, we'll come down to the, down below, and we'll kind of work that out and see what we get. So let's take the limit as t goes to 0 from the right of t natural log t. Yes, I left the minus up here. Okay, left it up there. We're going to figure out what this needs to be, what this is when we take that limit. So there's going to be a little work involved, so we need to, let's see what's going to go on. So if I'm approaching 0 from the right, that's 0. And then as t approaches 0 from the right, we've done it several times in this video. There's natural log. As I approach 0 from the right, this going to negative infinity. Well, I can't do 0 times negative infinity. So remember back when what you learned when you were doing L'Hopital's rule, we would rewrite this, the limit as t goes to 0 from the right, and that's going to be natural log t over 1 over t. And now you can see I have negative infinity over infinity here. See, this right here is negative infinity. See, as t goes to 0 from the right, that's negative infinity. This is infinity. This denominator here is getting smaller and smaller. This is staying at 1, so that's going to infinity. So I can apply L'Hopital's rule. And so this is going to be the limit as t goes to 0 from the right of 1 over t over, and then the derivative of 1 over t is negative 1 over t squared. And that is going to give me the limit as t goes to 0 from the right. And this is just 1 over t, right? 1 over t times negative t squared over 1 times the reciprocal. So this is going to be negative t, which is negative 0, which is 0. And so that tells us this term here goes to 0. All right. And so, well, let's look and see what we have. Well, that's 0 minus 0 minus 1, and then distribute this. That's going to be plus 0. All right. So hopefully all that made sense. And so this is just equal to negative 1. So, there's a lot to comprehend in this section. I don't know how many of you are still watching right now, but don't try to do everything. Don't try to do a bunch of steps in your head. You saw how I did on several of these problems. Some of these were easy to know what the limits were, and some of them, what did I do? I came down below and worked it. I went off to the side and worked it out. Okay? So just take your time doing it. And just remember, all you're doing here is you are evaluating the integral. Okay? So it's like you're working this, and then once you get finished with that, okay, then I take the limit of it. That's all it is. Okay? It's like until you get finished integrating and plugging your limits into the integral. Okay? And when I say that, I mean plugging in the 1 and the t in and get to this point. This limit, it's just tagging along for the ride, and then you just take the limit of it. So I hope this video helped. And if you need to, go back and review L'Hopital's rule. integration by parts, that stuff, use substitution. You've got to know how to do that, okay? And go check out my videos. I got a bunch of videos on that stuff. So I hope it helped. Thanks for watching. Check out my other videos, and I'll see you in the next one. Later.